Hello, I'm Peter Sandusky, and this is a sample lecture video being prepared and submitted as part of an application for a tenure track position at Cal Poly San Luis Obispo. The topic at hand is balancing redox reactions. Now, the intrinsic nature of redox reactions is such that one chemical reactant is going to be oxidized, that is, lose electrons. And another reactant is going to be reduced, meaning it gains electrons. Okay. So if you take a chemical like sulfite, SO3 minus 2, this chemical is added to wine to control fermentation. It's added to foods to retard spoilage. But it's a little bit tricky adding it quantitatively to material because sulfite reacts with molecular oxygen, O2. There's always some molecular oxygen around. And that produces SO4 minus 2 sulfate. Okay? And this is an oxidation reduction reaction. Okay? Now, in thinking about oxidation reduction reactions, the first thing is to determine which reactant is being oxidized and which reactant is being reduced. Okay? And we do that by assign oxidation levels. Okay. We're aided in assignment of oxidation levels by the rule that oxygen always has an oxidation level of 2 except for molecular oxygen where the oxidation is 0 or peroxide, something like H2O2 where the oxidation level is -1. So we don't have a peroxide here in this reaction, and we do have molecular oxygen, however. In all other cases, we can assign to oxygen an oxidation level of -2. Okay? And that allows us to determine the oxidation level in the sulfate, in the sulfur and the sulfite and the sulfate. So in the case of sulfite, the net charge on the ion is -2. We have 3 oxygens, and each of them have an oxidation level of -2. So that's going to be -6, which means the sulfur in the sulfite must have an oxidation level of +4, because +4 added to -6 is going to be -2. So writing the oxidation levels in red, the oxidation level of sulfur in sulfite is +4. Likewise, in the case of sulfur and sulfate, we have 4 oxygens, each with an oxidation level of -2, gives us -8. The net charge on the ion is -2, so the charge on the sulfur has to be +6. +6 minus 8 equals -2. Okay? So we can write in red the oxidation level of sulfur in the sulfate as +6. Okay? Now for oxygen, we can tell that the sulfur is going to be oxidized, which means that the molecular oxygen has to be reduced. Now molecular oxygen, O2, can take on some electrons and go to 2 oxygen anions like that, and that's going to take 4 electrons, okay, because the oxidation level of molecular oxygen, as we mentioned, is 0. The oxidation level of all other oxygens except peroxides is -2. Okay? Now from that, these oxidation levels we've assigned, we can then write oxidation reduction half reactions. So that's our next step, write oxidation and reduction half reactions. Okay. And so for sulfite going to sulfate, you have the sulfite with the sulfur at an oxidation level of +4 going to sulfate with the oxidation level of +6. And the only way that can happen is if the sulfur containing compounds are giving off 2 electrons. Okay? And this would be our oxidation half reaction. Okay. Oxygen with a molecular oxygen O2, an oxidation level of 0, would take on 4 electrons to go to 2 oxygen atoms with an oxidation level of -2. Okay. Now, so one characteristic feature of redox reactions is we can actually deal with these oxidation half reactions and reduction half reactions independently. Okay, and in doing that, what we have to make sure is that the electrons produced in the oxidation equal in number the electrons consumed in the reduction. Okay? And we do that by multiplying the oxidation and reduction half reactions by some integer, okay? So that the electrons consumed, 4 electrons reducing oxygen, balance the electrons produced in the oxidation of the sulfite. Okay, so clearly, if we just multiply this this oxidation half reaction of sulfite by 2, we'll have 4 electrons being produced and 4 electrons being consumed. Okay, we add the whole thing up. We would have 2SO3 minus 2 plus O2 goes to SO4 minus 2. The electrons would cancel. The oxygens produced are incorporated into the sulfate. Everything is nicely balanced. Okay? And the 3 steps we use is we assign the oxidation level in order to determine which was the which reactant was oxidized and which reactant was reduced. We wrote oxidation reduction half reactions, and then we multiplied the oxidation reduction half reactions by integers so that the electrons produced were balanced by the electrons consumed. Now, this example illustrates most of what's involved in writing a redox reaction, but let's consider one other case. As you can tell, it's sort of hairy to add sulfite to things like wine or food because you don't know how much you've added, because quite a bit of it's going to be consumed in this reaction with molecular oxygen. Okay? So you want to have analytical techniques for determining the concentration of sulfite in wine and food. And a lot of these techniques are based on the reaction of sulfite with triiodide, I3 minus 1. Triiodide, okay? And sulfite reacting with triiodide will produce sulfate and will produce iodide, I minus, okay? So we've already taken care of our oxidation half reaction. That's going to be sulfite going to sulfate plus 2 electrons, right, just as it was in the previous example. But the species reduced is this triiodide, okay? And this has an interesting aspect to it because you have one charge smeared over 3 atoms of the same element, okay? So the oxidation level of this is going to be minus 1/3 for each iodine atom in triiodide. And then it's going to be minus 1 for each iodide atom in iodide, okay? And so you can figure out that what you're going to have in this case is a consumption of 2 electrons to make that happen, okay? To take I3 minus 1 to 3I minus 1, okay? So we can just add without multiplying the half reactions, this would be the oxidation half reaction, this is the reduction half reaction. Just add these together, the electrons will cancel, and we have sulfite plus 1 molecule of sulfite plus 1 molecule of triiodide going to 1 molecule of sulfate plus 3 iodide ions, okay? And everything is pretty much balanced except we need 1 more oxygen atom. In other words, here we've got 3 oxygen atoms on the reactant side. On the product side, we have 4. Okay, so we're lacking one oxygen atom. So as step 4, you can add water, hydrogens, or hydroxides to balance atoms. Okay, so in this case, you would add 1 water molecule, and that would produce 2 free hydrogens, like that. And you'd have, on this side, you then should go back and count all of your atoms on both sides. On the reactant side, you have 1 sulfur. On the product side, you have 1 sulfur. On the reactant side, you have 3 iodines. On the product side, you have 3 iodines. On the reactant side, you have 4 oxygens. On the product side, you have 4 oxygens. On the reactant side, you have 2 hydrogens. On the product side, you have 2 hydrogens. Okay. Well, that about wraps it up for balancing redox reactions. I very much want to thank the search committee for asking me to submit this video. Thank you very much.